Good morning and good afternoon. Thank you so much for attending our webinar today. Our host will be Dr. Stacy Elliott. And before we begin, I just wanted to make a quick announcement that our team will be at the upcoming PEGS conference in Boston in May. And feel free to check out our social media platforms as well as our website for the latest blog posts, application note announcements, as well as every month's webinar. All right, without further ado, I'd like to introduce Dr. Stacy Elliott.
Thank you, Grace. Welcome in everybody to our April webinar. So today we're going to be talking about injectability. It's a topic we've covered before, but it's very popular and we have some new data to share with you today on the ability to predict injectability with our technology, with the VROC technology. So mainly we're going to focus on the importance of being able to obtain viscosity data at high shear rates. So I think it'll be clear as we move through how important it is to get that data over as broad of a shear rate range as possible. Okay, so just to do a quick overview of how this is going to be structured today, we're first going to give a quick review on what is viscosity, particularly how does our technology obtain a viscosity number. So our technology is VROC technology. Just for anyone who's not familiar with us or not familiar with the viscosity value. And then we're going to talk about analyzing fluid flow in a syringe, both for Newtonian and non-Newtonian fluids. And this whole process, which is going to take up a big portion of today's webinar, is going to be, this is how we're going to be able to predict that injection force, which is generally how we characterize the ability to inject or the injectability, how we're going to obtain that force from parameters that we know and the viscosity data that we have. So it's going to sort of clarify how all these parameters come together to give us that injection force value for those types of fluids. I'm going to put in there a quick clarity demonstration so that you can see how our analysis software, which we've named Clarity, can automatically do injection force predictions for you for Newtonian fluids. At the time, it's limited to Newtonian fluids, but I think it's still worth taking a look at so you understand how quickly you could do this type of thing in that software. And then we're going to go and do a more in-depth injection force analysis for non-Newtonian monoclonal antibody formulations where we can actually compare our predictions to experimental data that was obtained on these samples. So that's the agenda for today. Okay, so let's first go over what is steady shear viscosity and how does our particular technology obtain this viscosity value. So VROC stands for viscometer rheometer on a chip, and our technology is essentially a combination of microfluidics and MEMS, micro electromechanical sensors. And so we have a well-defined flow channel, microfluidic flow channel, and at the base of our channel are 4 pressure sensors. And we control flow rate through the channel and then measure the pressure drop across the length of the channel. And from these two values, in combination with the geometry of the channel, we can calculate the shear rate. So that's going to depend on that flow rate, which we're controlling, and then also the width and depth of the channel, which is fixed and well-defined. And then we can calculate stress from that pressure drop across the length of the channel, again in combination with the geometry of the channel. And from these two, we then calculate the shear stress, or sorry, the steady shear viscosity, which is defined as the shear stress over the shear rate. So this is what we mean in this conversation today. When I say viscosity, I'm talking about steady shear viscosity. And then this is how RioSense, our technology, obtains this viscosity value. And then when I share data later that I've collected, it was using this technology. And just a quick, we'll sort of address this a little more later. The microfluidic flow channel is ideal for measuring high shear rates because of the dimensions of the channel. Prevents any sort of turbulence or secondary flows that can be a real problem at higher shear rates and different types of instruments. And then also because it's the fluids is enclosed in this flow channel, you don't have issues also of sample flying out of your tool. So when we get into talking about how important it is to get high rates so that you can get good predictions for injection force, you're going to also want to consider how you're going to obtain those values. Okay, so let's start talking about injectability. So what am I talking about? I'm talking about, when we're looking at a fluid, particularly a therapeutic, and we're trying to determine, can we deliver this fluid by injection using a syringe? And generally, we'll decide whether it is injectable or not injectable based on the injection force. Some people, I think, if you look in the literature, they'll say that they don't limit, their criteria is not a force necessarily, but it's just the viscosity value. But hopefully you'll see when we go through today's talk that the viscosity is most certainly important, but it's also important to look at the geometry of your delivery mechanism because that's going to be very important as well in terms of whether it can be delivered. So I think the force is a more comprehensive criteria for you as opposed to just using viscosity alone. And the force does include the impact of that viscosity. So this force is basically what is it going to take to push this piston so that we can initiate and then sustain flow through our syringe. And so what's going to be important then is knowing what sort of flow do you want to deliver. And so this is going to be how much volume in what particular time. So volume is over time. And then it's going to have two components. It's going to have a friction component because obviously there's going to be some sort of friction between the piston and then the barrel of the syringe. So that's not something that we're predicting through calculation. That's something you'd have to obtain separately and will depend on the materials in your syringe package here. And then also if you do any sort of silicone coating to minimize friction, all of those will come into play and they're not something that we're predicting here. We're focusing on what I'm calling the viscous contribution to this injection force. And this exists because the fluid is going to resist flowing through this syringe. And this resistance to flow is going to be dependent on obviously the viscosity, because viscosity is a defined property that sort of measures the resistance of flow. And it's going to be dependent on whether that fluid is Newtonian or non-Newtonian. So Newtonian is shear rate independent. Non-Newtonian means that our viscosity will vary as a function of shear rate. The most common form of non-Newtonian behavior being shear thinning. And that's actually the examples we have today that will have shear thinning data. So I want to point out, keeping in mind, and again, trying to emphasize the importance of, knowing what rates are relevant and realizing that perhaps they could be quite high. If you do a quick estimate just using expressions from fluid mechanics for Newtonian fluids, you can easily go look up, and if you're really interested in understanding how the derivations that we go through today come about, I would recommend going and looking at some intro fluid mechanics books where you can actually review flow in a pipe or a tube. So a small, conduit with circular cross section, because that's basically what we're looking at. We're looking at flow in a very small pipe or tube. So you can find these relationships. So the shear rate, which is going to be related to that volumetric flow rate, and then the inner radius of whichever portion you're looking at. And it's going to be, that shear rate is going to be proportional to that inner radius to the inverse third power. So when you think about something like this needle, which has a very small inner radius, the shear rates in the needle can get quite high. So somewhere, depending on the needle gauge that you're using and how rapidly you're trying to deliver this, it's going to be somewhere in the tens of thousands to hundreds of thousands inverse seconds. So it can be quite high. And then also it's going to be dependent on the geometry of the system. So resistance will increase with increasing flow path length, and then also increase with decreasing internal radius. And then this is going to be something that produces a pressure drop from the piston to the exit point. So these are all the parameters that we're going to need to figure out how to deal with so that we can predict our injection force. So we're going to need to figure out how to incorporate properly the viscosity, the geometry, this pressure drop, and then the volumetric flow rate. So that's kind of the goal of the next few slides, is to really figure out how are we going to get a handle on this fluid flow through the syringe. Okay, so what we're going to do, the first thing we're going to do is we're actually going to go through a process where we see how we can simplify our calculation. And this is sort of a general simplification. I'm not making any big assumptions yet on whether things are Newtonian or non-Newtonian. So again, what we have here is this force on the piston to get the fluid moving. We're focusing on that viscous contribution. So looking at this, what we know, knowing that we're going to have this pressure drop that occurs as we get fluid motion up and running, that force on the piston is going to be that pressure drop across the whole flow path times the cross-sectional area of the piston. And this pressure is going to have different components because we have different components in series here. So we have the barrel, what I'm calling a transition zone, and a needle all in series. So it's going to just be something that we add up. So pressure drop across the barrel, transition, and the needle. Okay. So sorry, everyone. I've just got some word back from my team that you're not seeing the slides move. So let me see. Okay, so I think it's going well now. So I'm going to step back. I'm not going to repeat everything I said. I won't torture you in that manner. But I would like to just recap a couple things. Okay, so I think we don't need to do the overview again. Just a quick reminder. I went through sort of what our technology is. This is the VROC technology, the microfluidics, where we're controlling flow through our channel, and we have we're monitoring that pressure gradient across the channel with the sensors that are placed along the base. And this allows us to calculate the shear rates and shear stress, which, as we know, defines the steady shear viscosity with their proportionality. So this is our technology. And just then a quick recap here, injectability, we're looking at this fluid flow through the syringe, and we have to apply a force to basically initiate and sustain it. We're not dealing with the friction between the barrel and the piston. We're mainly focusing on this viscous part. So we need to understand what this viscous part will depend on. So it's going to depend on viscosity, which could potentially be experiencing very high shear rates in the needle. It's going to depend on the geometry, particularly length of any particular flow path and inner radius of that path. And then we're going to have this pressure drop that's going to exist from piston to exit of the needle. Okay, so I think this is hopefully we're caught up and we're on the right slide. Okay, so now we want to simplify things because what we have here is we have this this flow path from the barrel to the needle as it exits that have different lengths and different inner radii. So we don't really want to try to do an analysis of each section. So what this particular slide, what we're trying to do is look at it and say, can we simplify this in some manner and really zoom in on what's most important. So this force that we need to apply to the piston, this viscous contribution to the injection force, is going to be the cross-sectional area of the piston times the pressure drop across the channel, or the flow path, if you will. And so then this pressure drop has multiple components. So it's basically the barrel, the transition zone, and the needle in series. But again, as I said, we don't want to try to get in there and do analysis of all of these parts if we don't have to. So is there some way that we can simplify this? So if we look at the well-known fluid mechanics equations for Newtonian fluids, and again, we're using this as sort of a guideline to look at orders of magnitude, not necessarily fully committing to this being a Newtonian fluid yet. We're just using this to gauge how the pressure drop will vary in the different zones, so we can have some criteria for eliminating ones that aren't as important. So we know from the well-known laws of fluid mechanics that this pressure drop in any particular zone is going to depend on, it will depend on the flow rates and the viscosity, but what's going to change from zone to zone is the length of that zone and then the inner radius there. And you can see that what's most important really is that inner radius, which is dictating what the pressure drop will be to the inverse fourth power. So that's quite significant. And so if you think about how, if you go and sort of pull up some dimensions for, say, the inner radius of the needle, trying to deal with that transition zone in some way because it's not uniform in terms of radius across the length, and then the needle. What you'll find is that this pressure drop in the needle, because of that very small radius, is going to be significantly larger than the pressure drop in the others. It's very easy to convince yourself of that for the barrel, maybe a little harder for the transition zone because it's a little bit harder to characterize, but this is how many people try to handle this system and simplify it so it's not as complex. And so this is how we will proceed. We will proceed by basically assuming that the resistance in the needle is what's dominating. So now our viscous contribution to this force is going to be that pressure drop in the needle times the cross-sectional area of the piston, because we're still applying that force to the piston. So now, we know the dimensions of our syringe. Now we have to figure out how are we going to get this pressure drop that comes from forcing the fluid to flow through the syringe. So that's sort of the next step that we're going to do. So now we're going to look at how to do this just in general. Again, we're not really assuming that the fluid has any particular properties as of now. That use of that Newtonian fluid mechanics was really just to get an order of magnitude of what that pressure would be, which in this case is justified. So now what we're going to do is find a way to get this pressure drop. And so what we're going to do is now we're looking in the needle, because we know we're focusing on that. That's going to be the biggest contribution to that injection force here. And we're essentially just going to do a force balance, because we know that the force coming from that pressure drop is basically equal to the force, the steady shear viscous forces. And so how do we get this particular, how do we set up this force balance? So we know stress is force per unit area. And so we know the pressure drop, which is a normal stress, it's a stress, and then the relevant area that we need to multiply that by to get the force. And then the shear stress is going to be multiplied by basically the wetted surface area of the needle. So this is going to give us that viscous force, and then this is that force coming from the pressure drop. So this is basically, again, now we're getting it in terms of parameters that we understand and that we can work with. So we can sort of rearrange this to solve for that pressure drop, again, in terms of parameters that we can, some of them we already know, and some of them we're going to get from our viscosity data. Use that with our top equation here, and now we get sort of something that's general for the injection force. And so what we have to deal with now is this shear stress at the wall. So we don't get that necessarily immediately from our data, but we can figure out how to do that. And of course, we do know what the dimensions are of our test syringe. Okay, so now let's look at the simplest case, and that would be the injection force for a Newtonian fluid. And so we know that for a Newtonian fluid that we have this viscosity that's independent of shear rate. So our shear stress at the wall is just going to be equal to our viscosity, which is a constant value times the shear rate at the wall. And we know for Newtonian fluids that all of this flow in a pipe or tube is worked out and has expressions that we can use to calculate these things. So viscosity is constant, and what that ends up meaning is that the velocity profile in this tube or pipe is parabolic. And so there's a well-known expression for this from which we can easily calculate our shear rate, which is defined as that gradient in velocity perpendicular to flow. So, and we've already sort of seen this equation. I've already introduced it when we're talking about thinking about what types of shear rates do we need to consider when we're doing our experiments. So it's back now, and we can use that in combination with essentially this definition of viscosity to get our shear stress at the wall and get a very simple expression for this viscous contribution to the force for a Newtonian fluid. And it's just going to depend on that viscosity being constant, the needle length, volumetric flow rate, and then the radius of the piston and inner radius of the needle. So I wanted to, at the moment, just sort of step away for a moment from the PowerPoint and then go to our analysis software, which sort of does all of this injection force predictions automatically for Newtonian fluids. Just so you can get a feel for what our software is doing, but then also to see how easy it is to use that software to make some adjustments to you know, your parameters. So if perhaps your fluid is fixed and you can't change viscosity, but you have some flexibility in your delivery parameters, you can use this software to see how, say, changing needle gauge or changing what particular volumetric flow rate you want to deliver the product at, how that impacts this injection force. So I'm going to step aside here and use our analysis package, which we refer to as Clarity. So I'm going to stop the show for a second and go to Clarity. So hopefully, let me just check the panel. It looks like this is something you're seeing. So this is inside our analysis software, and I've already imported some of our viscosity data that we obtained on some monoclonal antibody formulations. And what we're looking at here then is this is our shear rates, and then this column here is our steady shear viscosity. And so you can see in this case, we have a range of shear rates, maybe from about 120 up to slightly less than 2,000 inverse seconds, and our viscosity is constant at about 40, slightly over 40 centipoise. And right now it's initially plotted here, viscosity is a function of shear rate, and you can see on this quite expanded scale that this would be considered Newtonian over this particular range of shear rates. But bear in mind, you know, we're only going up to slightly less than 2,000, and what we'll see later is it's going to be important to really explore beyond that. But the point of this really is to see the, you know, if you truly do have a Newtonian fluid, and there are certain injectables that are Newtonian, then you can use this most certainly to do some injection calculations. So what we do then is we just go and identify, here's our monoclonal antibody series and our analysis options. There are some others. We're going to focus on applying the injectability analysis with this little syringe there, so we hit on that. And just like that, we've already performed an analysis for the default parameters. And so when I close, what it's going to do is show me injection force as a function of viscosity. Now, because all of our viscosities are about the same, you know, all of these, although they're varying slightly as we change shear rate because of some noise, for the most part, you know, we have a constant viscosity and constant injection force. And what we can see is if we pop up this window here where we have the data, so it has all of these parameters that we just talked about that are going to be relevant. So the needle length, the inner diameter of the needle, the piston radius, or the, I guess it's using inner diameter. Okay, so the inner diameter of the needle or the inner diameter of the barrel, which would also be the diameter of the piston, and then the injection rate. So it sort of starts with some default parameters that, you know, are somewhat common, but these are something where you can now go in and say, okay, well, if I can't change my fluid, maybe I can change some of my delivery parameters. So if you have the ability to use a different needle gauge, for example, it's all programmed in here, so you can change to something, a needle gauge that would have a larger inner diameter, say. So I think, yeah, so if we change that to a lower gauge number or larger inner diameter, we can see how significantly the injection force can change with that. Likewise, if you have the ability to perhaps deliver a little more slowly, then again, you can change that as well. And this also will give you sort of what is the estimated shear rate in the needle for these parameters that you're selecting. And it's just using that equation that I just showed you from the Newtonian fluid mechanics. So, you know, we're seeing here for these particular parameters that the injection shear rate in the needle is going to be somewhere around 17,000. Now, we've only measured up to slightly less than 2,000. So we'd probably want to be confident that that Newtonian trend continues on up until the rates that's actually going to be relevant. And that it can for some materials, but for other materials, it may not. So that's something that you want to keep in mind. But this is a nice little tool for looking at how these parameters impact that force, and then also allows you to automatically calculate what is that shear rate in the needle, and have you collected enough data, or perhaps you need to collect some data at higher shear rates if you can. Okay, so with that in mind, I'm going to go back to our presentation. Okay, so now I've hinted at, there's a lot of materials that aren't Newtonian. We have a lot of non-Newtonian behavior, particularly in concentrated antibodies, but other formulations as well. And so we want to figure out how are we going to handle this for these particular cases. So we know now what we need is we need to somehow find a way to get this shear stress at the wall for our fluid flowing through our tube or our needle. And although for the Newtonian fluid, there's a well-defined parabolic velocity profile, which is how we calculate the shear stress, the shear rate being gradient perpendicular flow. Once we have something that's non-Newtonian, we now have some sort of irregular shaped profile. And it often looks something like this red curve that I've drawn out here for a shear thinning material, where it turns out that the shear rate at the wall tends to be higher for these shear thinning materials, and then more flat sort of collapsed shape towards the center. And it's really, there's only a few ways of getting an analytical expression for this, or only a few fluids that you can get an analytical expression for this. So beyond the Newtonian, something like a power law fluid, where you just have a power law across all rates that you're testing, then you could deal with this in an analytical way. But we're going to have to do it a little differently, because there's no clear defined velocity profile for us to do our calculations for something that, for a material that looks like this one here. So viscosity is a function of shear rate. What we have, and this is common for antibodies, is that you have this Newtonian plateau, and then ultimately an onset of non-Newtonian behavior, specifically shear thinning. So we don't have a way to deal with this as we just did with the Newtonian fluid. So we have to come up with some way from our viscosity data to get this shear stress at the wall, because we have everything else that we need. And so if you're thinking, is it really so important to worry about this? Do we really need to go to all this trouble, or can we just sort of deal with the viscosity on the Newtonian plateau zone? I'm going to sort of depart from all of the calculations for a minute and just talk about concentrated proteins, concentrated antibodies, and common behavior that we see for them. So just quickly looking at viscosity as a function of concentration, and realizing that many of the products that people are trying to deliver through injection are in the concentrated regime. And so that plateau viscosity that we just talked about, that's that Newtonian region before the onset of thinning. That's what we're looking at here with the eta sub naught. As a function of concentration, will ultimately, once you get to the higher concentrations, increase exponentially. And so, and the viscosities can get quite high. So, the important thing to notice here is that, as you get higher and higher concentrations and higher viscosities for these types of materials that we can approximate as colloidal, they interact very strongly. And these strong interactions, in addition to Brownian motion of these small molecules, that's the type of behavior that leads to shear thinning. So these are something that you would certainly expect could shear thin if you're dealing with them. And so what we're going to look at here, and you have to kind of wonder, you have these different types of antibodies where we've introduced different types of excipients to sort of modify or control their viscosity. You kind of have to wonder, I have a different antibody, I have a different excipient, I have a different concentration. So even though, say, this point and this point have essentially the same viscosity in the plateau zone, is that enough information for me to say that they're really going to behave the same way? Knowing what I know about antibodies and how they behave in formulation and what that means in terms of their rheological behavior. So And if you look at those, so all of those points that I just circled, what you can see is although in the particular instance that we're looking at here, that plateau value has a similar viscosity, but the shear thinning behavior is very different. So you can see that these two fluids, and these are two different antibodies, two different types of antibodies in solution prior to adding any sort of excipient, they have very similar plateau viscosities, but their shear thinning behavior is very different. So one of these shear thins by slightly more than 50%, and the other by maybe 10–12%. So is it really going to be enough to just focus on what's happening here in the plateau? And so let's sort of go through how we're going to deal with these types of materials, and then we'll show you what kind of predictions we get for these fluids. Okay, so bear with me, we just have a little bit of fluid mechanics left. Okay, so now we need to figure out how are we going to get this shear stress from the wall from our data. So that's what we need to figure out. So we need to figure out how we're going to get this shear stress from not only our data actually, but also our delivery parameters. We'll find out that it's related to that as well. So what we're going to do, and if you're familiar at all with the WRM correction, Weisenberg, Rabinowitz, Mooney, Rabinowitz, I can't remember all the names. But it's basically the correction that you need for certain types of inhomogeneous flows for non-Newtonian behavior. So you need it for our rectangular slit geometry, you need it for parallel plate geometry, anywhere where you don't have that uniform shear rate throughout the geometry. I'm going through a process that basically is kind of similar to that, but my goal is a little different. So if you ever sort of want to research this and look at how I sort of came about this, you can go back to looking at deriving the relationships to get your non-Newtonian correction. Okay, so what I'm starting with is basically I can calculate the volumetric flow rate that is going through my tube or my pipe by integrating the velocity profile across the radius. So this is just very simple. Basically, I'm getting this volumetric flow rate by looking at how the flow is across the radius of the tube. And so we do that, basically this is like an integral is like a sum. So I'm summing up all those fluid elements to get what the total volumetric flow rate is. Okay, so this still though isn't getting us too far. So now we need to figure out how are we going to get something that we can now relate better to our data, because we don't get velocity profiles from our data. So we can do some integration by parts. So that's something that you can easily look up and understand. It's just basically rearranging that integral so that it gives us something that we can work with. So now what we have is we have the negative of the derivative of that velocity. Okay, so that's, okay, now that's gonna ring a bell, because what is that? That is our shear rate. So now we can substitute in shear rate for this instead of leaving it in the form of a velocity gradient. And now we've made a little progress. But we still don't really have that shear rate as a function of radial position profile. So what can we do? If we go back, so if you go back to the sort of in fluid mechanics, if you're familiar with Navier-Stokes equations, that's kind of what you get if you take the momentum balance and make assumptions on Newtonian behavior. So if you go back to the point prior to where so you go back to all the governing equations prior to making that assumption, you can actually get a relationship for the shear stress as a function of radial position. So that is going to actually be linear across the radius, where it maxes out at the wall and goes to 0 in the center. And so now we can sort of insert this into our expression, and now we've got something that we can deal with. Because if you remember, viscosity is just the proportionality between that shear stress and shear rate. So if we have viscosity, we have shear stress, we have shear rate. So now we have it in terms of parameters that we can deal with. And so this would be also bringing in the inner radius of the needle. Okay, so one final step to get what we want. So as I mentioned, we can rearrange our data. We're used to looking at it as viscosity as shear rate, but we can plot shear rate as a function of shear stress. And if we do that, then we can fit a quadratic to the curve here. and then get a relationship between shear rate and shear stress. And for the particular types of antibody data that we're looking at, quadratic tends to work well. I've started working with some solutions which have different shear thinning behavior where, in the future I'm going to have to sort of modify this, but for proteins, antibodies, with that type of behavior that we already saw, this seems to work well. So if we fit our data, then with this quadratic fit, then we can essentially get a quadratic equation for the shear rate the shear stress at the wall in terms of our data fitting parameters, volumetric flow rate, and inner radius of the needle. And of course, this is very easy to solve. And you only have one root that is relevant. And so now from basically just we generate our data, we do the curve fitting to get our parameters there, and then we know what sort of flow rate and radius of the needle that we have, and we can then get this shear stress at the wall. And then this allows us to get our viscous contribution to the injection force. Okay, so just now that we're going to start showing some more data and sort of our analysis, I'll just point out we've already kind of covered our core technology and how we internally measure viscosity. One of our products that incorporates the VREC technology is our Initium 1 Plus, which is our automated system. This is what we were able to utilize for our measurements here, where we're able to do all of these automatically on a very small volume. Because of our retrieval feature, we can load the sample, and once our test syringe is empty, we can then retrieve that and continue testing. So it's a way of getting all of our data points that I'm about to share with that sort of small volume, and it's also in the enclosed environment, so we're not worried about evaporation. And as I said, in some of the cases, we're going up to quite high shear rates, and our particular microfluidic technology is not prone to turbulence or secondary flows. Okay, so let's go back to, before we do a more broad analysis, let's go back to those curves that I pulled up before, where we were seeing that, okay, that plateau value was nearly the same, but thinning behavior was quite different. So do we really need to do any kind of more extensive analysis, or can we get away with just doing maybe a viscosity measurement at 1,000 or 2,000, 3,000 and use that? So what I did was I took the data and I did basically that analysis that I just provided you with for the non-Newtonian fluid using some parameters here, delivery parameters, and I estimated what would the predicted injection force be. And we'll see in a moment when I compare predicted to measured that these are good ballpark figures. And certainly the trend that we're looking at is consistent. So what we're seeing is that even though this particular fluid represented by the green points, this MAB3 without excipient, is a tad higher in low shear plateau viscosity, it's the prediction for the injection force is actually lower than this MAB2 data without excipient. And the reason being is that it shear thins so dramatically over the course of the measurement here. And in fact, what's most important is the data out in this high shear rate zone, because that's what the fluid will be experiencing in the needle. So although these two are very comparable in the low shear rate range, they are not in the high shear rate range, and that's really what's important when you're looking at flow through that needle with a very small inner radius. So I wanted to sort of point that out, that this is how you can understand, just from a qualitative perspective, why this data is so important for the prediction. Okay, so now what we're going to do is going to sort of run a broad comparison where we've had many formulations, and those few formulations that I just showed you are in this massive data set. And we basically generated shear rate sweeps for all of these samples. I think there's 18 here using our Initium with some multiple flow channels. And we see a very broad range of behavior, everything from maybe say 5 centipoise up to nearly 85 centipoise, and also a range of shear thinning behavior, and a number of examples where we have situations where the plateaus are very similar, but the shear thinning zones are quite different. That depending on the type of antibody, and then also the type of excipient. If you've introduced one, they all impact this. So what we do then is we take, just to sort of show how the predictions can vary, we're going to do the injection force prediction, and we're actually going to include the experimentally obtained friction component of that. So our collaborators obtained that friction component by measuring an empty syringe to get some gauge of what that barrel piston friction would be. And then we added that on to our viscous part, which we predicted in two ways. One being using just that Newtonian plateau, using the Newtonian equation, one being using the full shear rate dependent viscosity that we got and that non-Newtonian analysis, where we do some curve fitting to our data to then calculate that shear stress at the wall, which then gives us our force. And so what we see then is if we look at measured force as a function of predicted force, the blue line in the center, diagonal line in the center here, if everything collapsed on there, then we'd be predicting perfectly what was measured. And so let's look first at the Newtonian plateau, and we can see that we do get some data points here that are predicted well. And of course, if you remember back, we'll just jump back. Some of these products don't shear thin substantially in comparison to others. And it's a little hard to tell, but there are a couple of them with the very low viscosities that are actually Newtonian. So that's not too surprising. But what we'll see then is there are a number of data points where we're really grossly over predicting that injection force. And in some cases, we're predicting something maybe 125 newtons when in reality it's only about 45. So that's quite a large over prediction. And this could be a situation where you disregard or dispose of a particular sample that could be utilized in your delivery system if you're not taking into account this extreme shear thinning behavior that can occur for some of these fluids. So then what we do is the full non-Newtonian analysis, and then we see that the data points shift over to these blue data points. And now we're getting something that is much better. We will see, however, that we do underpredict a little bit in some instances. So initially we were grossly over predicting when we were ignoring all the shear thinning, and then when we incorporated it, we did perhaps underpredict a little bit. But the difference now, it's still quite a big improvement in terms of your prediction, and I think still a benefit to go through the full analysis. So sort of one final comment that I'll make is, what are some of these potential causes for this under prediction that we may sort of want to look at in the future and try to improve upon. So one thing, if you think back to our very first sort of simplification that we had, is we really wanted to simplify all of the calculations because they could have been even more tedious than they were. So what we did was we sort of ignored, we didn't really deal with this transition zone because it's a little harder to deal with. It's very easy to make the comparison to what's happening in the barrel to what's happening in the needle, a little more difficult in this transition zone. So, the question is there some way, is this important? And is there some way we can incorporate it? I think some people who have the ability to do computational fluid dynamics can analyze it in quite a bit of detail, but that's kind of beyond our scope here. So, we might want to think in the future, is there some way that we can include it? And, because, as we go from zone to zone, we're seeing a change in the radius of the path. That could also impose some sort of extensional type of deformation where we're seeing some gradients in velocity parallel to flow. So there may be different ways of exploring that and trying to figure out if it's important or not. The other reason that we may be under predicting there is that in the end, it's involving, our data fitting is involving an extrapolation. So here's an example of one of the curves that we saw before that's part of all of that analysis. And we have the viscosity as a function of shear rate. And what we can see is if we actually calculate what the shear rate in the needle would be, it's going to be somewhere around 300,000. So although we did a pretty good job of getting to high rates, we got up to maybe, I think it's 60,000 there or so, 50, 60,000. We didn't quite make it to where we needed to go. And so we did have to extrapolate. And so our curve fitting, and so the right plot here is just another way of viewing our data. And when we did the analysis, we had to extrapolate this to that particular shear rate. And what may be happening here is when we extrapolate, we're basically assuming that this power law decrease in viscosity is continuing on up to this 300,000 inverse seconds, when in reality, there may be an inflection point there where we start seeing a plateau in the viscosity. Because if you're familiar with protein systems, which behave very similar to colloidal systems, eventually, if you can get to high enough shear rate, you will see a second plateau emerging, which would be that high shear rate limiting plateau. So the concern maybe is with our calculations here that we're extrapolating and maybe underestimating what that viscosity might be, if perhaps in reality it's really starting to plateau here. So that could be something that we could look into. And there are certain formulations that we sort of maxed out on shear rate because we maxed out on flow rate, whereas others we maxed out because of pressure limitations. So on the ones that we maxed out on flow rate, we can actually sort of start investigating this by using our new instrument, which was just released, the MVROC2, which has a broader flow rate range. So hopefully in the future, we'll start to address and see if that is one of the major factors. So I'll stop there, and thank you for joining us today. And my apologies for the confusion at the beginning. Hopefully, with that quick review of what was said, you were able to catch up and follow along. So what I'll do now is open and see if there are any questions. Okay, so let me get through all the ones saying you don't see the slides. And while I'm scanning through these real quick, I'm not sure if Grace mentioned it at the beginning, but everyone that attended will get an email with a link to the recording and the slides, so you can always review those. And then if you have additional questions, you can check in with us. Okay, so there is a question about the shear thinning behavior. Is shear thinning behavior a predictor of stability? Not necessarily, no. So shear thinning can come from, so let's just use the particular types of formulations that we were talking about. We're talking about those protein antibody formulations, which we can roughly model as colloids. And you can have shear thinning behavior from either strong repulsive interactions or strong, or even not even strong, but moderate attractive interactions. So positive interactions and attractive interactions can lead to shear thinning. However, those repulsive interactions are very stabilizing. So something that shear thins very dramatically due to, so say, a large electrostatic repulsion would have, a lot of shear thinning, but it would be very stable because that's a stabilizing mechanism. Whereas something that shear thins because it's attractive and it's forming aggregates or clusters, then that one is not going to be stable. So shear thinning alone, because you can have shear thinning from those different mechanisms, is not entirely an indicator of stability. What you'd want to look at more is, I think, how does that behavior change as a function of time? So if you're interested in maybe storage stability, you could monitor that behavior as a function of time. And we've done that type of monitoring, and we have seen that viscosity change specifically increase as the material aged and presumably became more aggregated. Okay, so there's a question about trying to relate this topic to ink formulations and whether they can be ejected up, I guess, from the print head. So this is different type of analysis, I would say. Yeah, that flow is driven in a different way. So the fluid mechanics would be somewhat similar. You still have flow in the tube or the pipe type geometry, but you're going to have to look at the different driving force, the mechanism that's driving that, and how that's varied. And also in terms of the inks coming from the nozzle, say, any sort of extensional component that comes from, first that narrowing and then the filament formation. So there isn't a direct analogy for ink at this time, but you could, approach it in a similar way in the sense that it's still flow through that particular type of geometry. Okay, so there's a question about the transition zone and how to analyze that. So someone is suggesting that one way to do this is to utilize the lubrication approximation in fluid mechanics. So yes, I think potentially. I haven't tried this one yet, but I think that could be something worth looking into. But yeah, I can't comment and say for certain that it would work because I haven't actually tried it. But thank you for the suggestion. Okay, so then there's a question about considering injections when you're doing different types of injections. So this would be subcutaneous versus IV administration. So I would say, yes, there would be different considerations here. And of course, it's all going to depend on things such as the needle gauge and the sort of rate that you're administering these. So I'm not too familiar with parameters in IV administration, but I have heard different comments from customers about subcutaneous. And of course, they tend to vary quite a bit. And I've heard everything from people want something 15 newtons or less, other people are willing to take maybe 30, 40 newtons. So I think it's a kind of a gray area in terms of, is there an exact number for every application? It seems that there's not. It seems that people are willing to tolerate different variables. But to rein myself in, I would say that you would view these differently, and what you would want to look at is that, dimensions of that flow path, those needles that we'd use in the different applications, and the rates at which the fluids would be delivered. Okay, so then there's another question about someone's looking for some references perhaps where excipients were evaluated for their ability to actually reduce the viscosity for injectables. I do know of some publications where they look at excipients reducing viscosity specifically, but I don't think that the publications I'm thinking of actually went to the trouble of calculating an injection force for those reductions. And I think maybe they didn't do that because, as I just mentioned, there are so many delivery systems and they vary quite a bit. So depending on how you're delivering it, you could be doing it with a different gauge needle, and therefore perhaps, taking that viscosity data and, doing a calculation to make grand conclusions on injectability maybe isn't appropriate because it, one product could work for some person and maybe not for another. So I can, direct you towards, as I said, excipients reducing viscosity, but I haven't really seen where they show for a particular system how that impacts injectability. Although, just to follow up on that, that's certainly an analysis that you could do on your own if you're doing a variety of excipients, just as I sort of described there. And let me actually quickly step back, because basically all of these materials, we're looking at So these green curves that I've pulled back up here, this is basically something that's very similar in concentration without excipient up here and then with excipient down here. So, we can see how that fluid viscosity curve changes with shear rates, and then we can see how our prediction of the injection force changes with the introduction of that excipient. And likewise with our other type of antibody formulation, we can see how that changes. So, and of course, this is, as I stated, for a very specific delivery system. So you could then, adjust this for your needs. But, you could do that calculation for yourself. Okay, let me see. I think we've covered all the questions. I'll just take a quick look and make sure I didn't miss any. Okay, so I think that was the last one. So again, thank you for joining us, and thanks for your patience with the slides there at the beginning. And as I stated, you will get a link to get the recording and the slides. So if you wanted to take a look at what maybe wasn't clear at the beginning, then you're welcome to do so. So thank you very much and enjoy the rest of your day.